Hidden in plain sight, processes shape everything around us, from the transitions inside atoms all the way up to the workings of humans and machines. They're the building blocks of systems, ticking away at their own pace, faster here, slower there. Their changes shape space by laying down memories to build on later. We find process agents at every scale, their stories unfolding as separate lanes, but if able to share and observe one another, they can signal and coordinate, weaving changes into patterns of shared outcome. That's how systems form. Paradoxically, perhaps, the underappreciated arbiter of change is repetition. Cycles are what distinguish the regular from the unexpected, and it's by comparing a repeating loop to something new that we can measure progress and link singular events into ongoing dialogues. Understanding networks is the goal of science, and putting them to work is the aim of technology. Spinning, mixing and wiring the world together, memory by memory, symbol by symbol, and layer by layer, processes weave networks into engines of progress to make systems that are bigger, faster, and smarter.
Fell in love with the internet when I was 17 and really wanted to study it, figure out how to study it. They were still building it, so although there was definitely some research going on in, applying queuing theory to a packet switch network, there wasn't, the network was growing faster than the science of the network, let's put it that way. That's been true ever since.
The value you create and the connection or the resonance with the human ambition that those networks can form, does that allow us to look at the world in a different way? But as humans, does it allow us to experience that? And the answer is very definitely yes.
People value things that are closer to them more than things which are further away. Doesn't mean the things which are further away are less important. If I want a cup of tea, believe me, power is critically important in me getting a cup of tea. I might value the cup of tea more than I do the power because the power is just less visible to me. I don't see it. A consumer has a need for a cup of tea, but a cup of tea has needs. It needs a cup, it needs tea, it needs hot water. Hot water has needs. It needs cold water, it needs a kettle. A kettle has needs, power. So what we've got is an anchor in terms of the user, and we've got position described through a chain of needs. It's a metaphor for distance almost. So, for example, when you go into a tea shop, your cup of tea is very visible to you. The power used to power the kettle to heat the water to make the cup of tea is not very visible to you, so it's far away. So visibility is actually within the chain.
So the battle between the sort of structures of what we're talking about as a society have already been, I wouldn't say disrupted, but there's other structures that run completely alongside it with that network effect, powered by technology, enabled by technology, but not because the technology matters, but because the technology allows that human connection and supports that human connection. And therefore it's a resonant way of humans working together in this collaboration economy that I call empathy economy.
Later on, after 9/11, when Homeland Security Department was created, and there was recognition that we really didn't understand the internet, and it was now going to be a source of a theater for activities that were going to potentially create harm. So they invested money in projects to allow data sharing and measurement and mapping, and that was CADA.
Every time you do a write in Azure, say an Azure Blob or an Azure Disk, it goes to 3 separate locations before it returns. Now those 3 separate locations are typically 3 separate racks, although you can configure it to say, hey, it has to be 3 separate buildings, okay? So that having, you do a write, an entire building can collapse the very next second and you still have 2 copies.
Some networks are fixed in space, solid rigging for information. Others are virtual and less obvious, relying on chance meetings in a fluid state, as in meeting places. Whatever their form, they have repeating patterns that give them their special powers. Star configurations have a central hub that anchors a number of satellite nodes to a common leader. Stars of stars form hierarchies that have branching processes forming tree-like explosions. Meshes are grid-like webs with multiple routes between each points, robust and redundant. By short-circuiting barriers to cooperation, networks plug processes together to make new things. It can be a slow business at first, as parts work through the complexities of finding a common language. To make processes faster, we need to figure out how to make them simpler, more elementary, smaller in scope if not in size. To make them bigger, to explore and serve larger populations, they have to be enlarged without adding the complexity that slows them down. Finally, to make smart processes, they have to recognize context by recalling prior experience, drawing on the memories laid down across former paths. Bigger, faster, and smarter aren't always compatible goals, but as long as everything moves in step, we can make appropriate trade-offs without sacrificing too much.
For scaling, they created regional networks for the research and education community when this was really just a research and education infrastructure. And then those regional networks were responsible for connecting up the universities, which were the end customers in the internet space. So you had a pretty hierarchical structure. That structure persisted for a while when the commercialization and privatization of the internet happened. But in the 90s and the beginning of the noughts, you started to get a bit of breakdown of that structure, and you had more of a meshy connection where many of the regional, what we call regional networks today, you might call them mid-tier or intermediate networks, they would connect with each other enough that they really didn't need to be paying transit to the upper levels. And that put a lot of pressure on this, what we call the transit industry. Still is the case today.
There are scaling factors at various levels. Physically, there are networking architectures that are helping you scale, like horizontally scale, like the CLOS architecture that is very popular in today's data centers. What it allows you to do is add additional capacity to your network, physical network, add more servers to your data center.
Systems involve exchanges of information that fit together to tell a larger story. Information is about symbols, in other words, names and characteristics. Each connected agent needs some memory to recognize symbols around it. To recognize anything, agents depend on being able to divide the world into parts that can be assigned labels.
Stigmergy, S-T-I-G-M-E-R-G-Y. What is it, right? It's the broadcasting, one way unilateral broadcasting of information, a one-to-many communication between agents, where the communication doesn't require a reply, it's more of a broadcast. Anyone who's interested can pick up the information and use it in a way that's meaningful to them. Ants leave pheromone trails. Those trails lead to food. That's a stigmergic process.
As information grows, no agent can have enough memory to remember everything around it. But networks allow a workaround by partitioning into cells. By slicing up a network with imaginary boundaries, agents can take ownership of the information real estate to cultivate their own meanings. An index is a name that points to a collection of related memories. By grouping and ordering things that make similar promises, we form categories, reservoirs, folders, and catalogs that trade individuality for bulk identity, so that we can refer to everything in a particular category by a single name, or perhaps a number for repeated amount.
Architecture, but now you have all these chatty neighbors, and how do you constrain that? The one thing is definitely you can limit the number of people into groups, so constrain your chattiness. And in networks, these are called broadcast domains. So these are not only providing isolation for traffic, they're also reducing the broadcast domain. And these are constructs that help you build a hierarchical network.
If you go to biology, for example, if we remove the nucleus of a cell, the cell will continue to live for quite a while. But if you breach the boundary, the cell wall, well, that cell, out it goes, right? So.
All agents have a limited capacity to learn and distinguish identity. Luckily, space is mostly empty. Information is sparse, making it viable for agents to recognize a range of symbols from their networked neighbors. But as space fills up, the economics of memory become strained, and agents need to ignore information or collaborate to physically extend their interior capabilities. Busy networks, rich information, increased size, slower pace. Being connected to information isn't always a blessing. Without identifiable features, space would be a formless and indistinguishable snowstorm. What we call noise isn't the lack of information, but rather so much that it exceeds the limits of what can be distinguished with limited faculties. In information science, the loss of distinguishability goes by the name of entropy. It's a catch-all term for an ongoing tension between scale and meaning. Although every snowflake is unique, at this scale our limited faculties see only a blur of white. We attribute significance or meaning only to information that stands out clearly against an empty background to be useful. Meaning is an economic defense against unprocessable information. Agents isolate themselves from unwanted noise using boundaries to protect their meaning. These protected kernels limit access to the memories that determine process. That's true in computers, in biological cells, in boardrooms and in towns. But is it fair to compare computers with cities? Apart from the differences in scale, the kinds of process are very similar. We design cities like microchips as batteries of places labeled by their function, producing information as goods and services and wired together by networks for access to input and output.
It's largely constructed, right, through the rule set. So, for example, if we worked in a corporation, let's say that you're the visiting consultant and I'm a person who works in this organization. When you come and visit and I introduce you to people, the first thing I tell you is where they sit in the organization, right, in authority terms. Oh, this one reports to Mary, our CEO, and then Bob reports to him, so it goes Mary, Matt, and Bob. So that actually locates you in the authority distribution schema. You know where you are. That information is kind of a glue that holds things together.
This is the old Grandpa's axe paradox, right? Oh, Grandpa's axe is amazing. It's been in the family for 150 years. It just keeps going. Really? Yeah. We've changed the handle 5 times and the head 10 times, but that axe just keeps on going, right? So, well, wait a second. So at some point, you've changed all the parts, but you kept the identity.
Meaning begins with names. Some names are given, others are implicit in the shape and function of objects. Function is a form of information, and information is a form of function. Same name, same function, or unique name, unique individual.
Namespace is a coordinate system. So once I have a name, an identity, and I have a name, and then I have a namespace, the question is, well, what's the use of the namespace? And it's, well, to find things, to have a handle that I give to someone else. And the challenge with namespaces is there's often some sort of a containment hierarchy. Like now let's go back to operating systems. I put a file somewhere. Well, where did I put it? Well, obviously I did it by project, and then by date, and then by project lead. Like, well, I don't know what date it was. Well, you're out of luck, right? Now you have to search. So if you and I have the same cognitive model, a namespace works very well. If we don't have the same cognitive model, then the ability to say, well, a particular item can exist in multiple namespaces, or I have search. Well, it turns out that then we're also adding the idea of namespace mapping or graph traversals. So it's not just a containment hierarchy where a particular node contains other things, but a particular node has relationships to other nodes in the graph. And then you can navigate those things. So you can navigate to a person and then navigate to their documents, or navigate to their peers or to their managers or to their appointments. And then having gone to a document, you can navigate to the other people associated with the document or the meetings where that document was presented. So you have graph traversal.
So a fundamental difference between a graph and a map is in a graph, what you've got are almost like a node and spoke diagram. You've got the relationship of things, or one thing to another thing. The distinction between that and a map is in a map, space has meaning. So where you position those pieces actually matters as well. When you look at any form of map, you need three basic components in order to explain space. And those components are an anchor, like north, position of pieces relative to that anchor. This is north, south, east, or west of that. And you need consistency of movement. So if I go north, I'm going north, I'm not going south.
So that's some crazy powerful stuff. But now what we're doing is we're adding synthetic nodes to facilitate graph traversal. Okay, so literally what we're doing is we're using artificial intelligence to mine all the artifacts in the system, documents, emails, chats, etc. And we're saying, hey, we think that there's a synthetic thing, a project, and we'll create a node in the graph, and then that project then associates a group of people, a set of documents, a set of meetings. So now all of a sudden we're synthesizing nodes in the graph to make graph traversal easier. It's a database view.
Maps are imperfect representations of the space, and all maps have to be imperfect representations. A simple example of this perfect map of France would be 1-to-1 scale, which means it would be the size of France, and therefore it would be France. So at which point it's useless. In order to be useful, a map has to be an imperfect representation of what it's describing. But if you have a story about what's going to happen and you put it on a map, and I challenge the map, I'm now no longer challenging you.
So it turns out that IP addresses are a great domain. There's IPv4 and IPv6, right? IPv4, they both have different challenges, right? IPv4 is a limited set, but for the limited set, you sort of know what an IP address means, right? So which says, say, given an IP address, I can kind of tell you where it is, right? But with IPv6, now I can name everything in the universe many, many times. So it's a great namespace for that. But the meaning of the name no longer has the semantics anymore, right? Because an IPv6 address could be anywhere. So it really doesn't tell you anything. So often you have this challenge between space and semantics.
And really pretty soon out of the gate into commercialization, they realized, we weren't really thinking of global use of the IP protocol. So there's not really enough addresses for everybody on the planet. There's not enough, the equivalent of phone numbers. And so they created some stopgap measures, realizing that these were only going to be temporary in order to make the address space last longer. Now, address space allocation is not the kind of thing you can just throw over to the private sector and say, okay, let competition, let market forces work this out. Much like phone numbers, you need to have some agreement over that when you call a phone number, you're going to get the person who owns that phone number and not somebody else who's decided that that's their phone number today. Although you can imagine there are 4 billion IP addresses in the IPv4 space, you can imagine giving one out to everybody and that gets you at least half of the population of the world. It doesn't work that way because of the way the routing system has to scale. They would give out addresses in chunks. And in order to make the routing system scale, they would give out addresses in contiguous chunks, just like you'll get a prefix and a phone number where everything in the building starts with a common prefix so that your internal phone system is somewhat sane. They would do the same thing with addresses. And every router had to maintain paths to some set of addresses on the internet. And in order for that routing table to stay within the physical bounds of what router companies could build at the time, they would try to limit the number of routes in the routing table. Each route gives you a path to a set of addresses that we call a prefix in routing speak.
Networks allow us to revisit patterns of memory by associating different routes through space and time with identity and context. A machine is basically a network for repeatedly routing influence in a regular way through a system of cause and effect.
You will see event loops at multiple levels in a system, At the lowest level, like I mentioned, it could be your interrupt service routine, right? Like a network packet coming in. It's a queue. Essentially, it's a queue, and application is in running an event loop to drain the queue and get what it needs. So yes, event loops at multiple levels. Even the applications are multi-layered, right? For example, a load balancer. An application is not a single application, but it has a lot of worker nodes to do the real thing. So then there is an event loop at the next level. The kernel is the core of the operating system, which is highly privileged. When I say privileged, it means that it has access to hardware, it has access to CPU and all that. And this access is not given to anybody else, like a random application or a user space application. So in CPU architectures, usually there are hardware controlled privilege levels. They're usually called rings. The kernel runs at ring 0, the lowest level, which is the highest privilege, which means kernel has all access to the hardware. It doesn't give control easily to a user space.
Event loops filter information a bit like a hotel service desk, waiting to route new arrivals to allocated rooms, unique destinations for unique interpretations of identity. The more networks grow in sophistication, the more memory they need to recognize the meanings of events, pushing boundaries and internal costs up. Information recognition costs energy, and that cost is starting to be a toll on our modern world.
CPUs have increased 5 orders of magnitude during my career. It is my subjective experience that the computer performance has increased by well less than 1 order of magnitude. There are 4 orders of magnitude of performance gone unaccounted for, and you should find them and get them back for us and you'll get rich. And indeed, I think what we've done is, Moore's law led to a lot of sloppy programming and abstractions on top of abstractions on top of abstractions. And hey, it got us to where we are. But I do believe that there are literally orders of magnitude of performance gone unaccounted for, and that we can go and harvest and reduce the energy per answer. So that's number one thing.
You have this peer-to-peer architecture. So really, if you're trying to do security in a peer-to-peer architecture, you're trying to secure the channel between 2 endpoints. That turns out to be really hard when you've got middle boxes in between the endpoints. You don't really have endpoints anymore. I don't know where the content is that I'm downloading. It's on some cache that's inside my access provider's network. So how is that end-to-end? It's the whole end-to-end model has kind of gotten compromised by the content distribution focus of the current internet. So the name data networking and a lot of other, they call it information-centric networking, is sort of the subfield of network architecture design, of which NDN is one example, are about, instead of trying to secure the channel, instead of even thinking about it in terms of channels, is you think about it in terms of the content.
As part of this process, you not only have collectives and values, you also have enablement systems to help diffuse those values. And one of those enablement systems is the use of propaganda.
They're basically trust management issues, and trust management is basically a not technical problem. It's basically a sociological problem that we need, admittedly, really good technology in order to solve them, but you also need awareness of how to handle the sociology aspects of it. That trust is really about people.
So most people are consumers of the tech that actually connect us, but that technology is actually owned largely by private individuals or corporations. And essentially, it endeavors to be a walled garden. It endeavors to corral humans and society within its boundaries and penalizes the technology itself. The algorithms are designed to penalize you were you to stray, or were you to infect that walled garden with seeds from elsewhere.
As networks climb the layers of scale, building their service abstractions, what's apparently offered and what's perceived are not always in perfect alignment. In every promise binding, there's the potential for misunderstanding and even abuse. The darker side of networks is something we prefer to ignore, but information is nothing without interpretation. Is a broadcast to quench a need or to flood and overwhelm? Advertisement or suggestion? Opportunity or subjugation? Every intention, good or bad, can be subverted by a network that encapsulates it. Since the millennium, we've been reminded on several occasions of the power of network epidemics, where disease plugs into unwary promises to accept. It applies to computer viruses and other malware too. If any signal becomes too strong within a system, it can obscure other information and disrupt the pathways of reasoning, whitewashing delicate nuance or burying information in more information like a garbage heap. Imagine if we never reused the houses and things of those who had died. Today, the photos and personal junk of 8 billion people are just about manageable with the most advanced technology. But if we don't forget some of that information soon, it will eventually overwhelm our capacity to find what matters. And the cost in terms of energy would begin to dominate climate change. Network meeting places, also called hubs, are the primordial soup of innovation. As long as processes can interact, potential partners can find their match to catalyze new ideas. And where different networks meet, social, physical, or electronic, far distant ideas can suddenly be local in your neighborhood, bringing the chain of needs or dependencies to become global.
I think both, because people have seen you on Facebook and they meet you. Oh, was it you? Because you are a friend of a friend of a friend of a friend. I have heard about this product. I've heard about your story. So internet is the right tool to use.
Here in Tampa Bay, the Oxford Exchange was once part of a meeting place for wealthy Victorian railway magnates during the age of steam. Today, it's a magnet for social networks of a different kind. It still plays the role of a business hub connecting possibility and opportunity.
Still working with women. While working with them with the ginger, we can also introduce the digitalization, like saving money, loan. I think that the thing is that people have to understand it. Once they understand it, they believe in it. And what I saw is that they are not 100% in digitalization. They're so afraid. When you say digitalization, oh, no, that's for, I said, no. It's here for everybody, everywhere. I had a meeting yesterday with 10 people in different countries. They went, that's what you see.
Hubs like this are the catalysts for new business, routing ideas along useful paths. A hub could be a place or a person. Networks probe and connect the world's experimental circuitry, and they play a major role in machine intelligence. But connecting things together is not enough. The promises needed to start something aren't necessarily the ones needed to sustain it over time.
So one of the economic patterns that I like is something called this peace, war, and wonder cycle. So it's all to do with industrialization of technology. So the big changes in society never happen with the generation of the novel and new, the genesis of stuff. It's always when something which was pre-existing becomes more of a commodity utility.
Putting things together is no guarantee of success. All systems have to adapt to prevailing conditions. Just as the properties of materials, metals, glass, liquids, are a result of the kinds of molecular networks they form, the same could be said of societies too. When bonds are inflexible, systems are brittle and may fail suddenly, shattering into pieces. If more plastic and adaptable, they may survive shocks and even rebound.
Africa is poor because the women in Africa are poor. So once the women get access to financing, access to education, access to work, I think there's many things that will change.
Life itself is both engineering and ecologically resilient. It can cope with a broad range of environments, and when things are parts of it are destroyed, life itself, other components will adapt, take over that area. I would suspect that what we've got in the banking system is lots of engineering and very low level of ecological resilience. And the way you normally spot that is ecologically resilient systems are very diverse in nature.
Mobile banking is going, to the sky.
We have over 50% of humanity that is connected online. So that has changed the dynamic about how socially we network. And whilst the walled gardens, what I call the social machines that monetize us as the product, have that business model. And it's usually a freemium model these days. It's not just a free model as it might have been in 2000, as it often was in 2009. As part of that monetization, there's a paid element, which actually allows you more access, but obviously enriches that platform and the network. So essentially, as a society, these social machines have corralled and contained us, and that human interaction works within those rules.
Am I who I say I am? Do I really have a right to use this IP address? Do I have a right to announce these addresses from this AS? Is this actually the path? Am I lying about the path that I got from all of these other ASs that I'm now propagating to you? All of those are promises, and they are relatively trivial now for bad guys to subvert. And so what we've been trying to do for the last 25 years is figure out how to add more real trust anchored into the real world into those promises. And that's been really hard because it's where technology meets the real world, and the real world problems are much harder to solve.
Well, if I understand it, it is about being clear about contracts and objectives, protocols, and processes. I talked about a model where I say I perform these steps and I get a desired result. That works as long as you control everything. But there are various things where you don't control something, okay? And where there's some external process or something out of your scope of control. And therefore, if you do the same steps, you might get a different result. And so in those environments, what you want to do is to say, well, actually what I want to do is I want to focus in on the objective. What is my goal? And then determine the steps required to meet that goal. And therefore, as things change, you continually go towards that goal.
Promise theory is in there, whether you like it or not. It's just that we're not really coming to terms with how do we tie these promises to the real world. All right, we've effectively tried to have these promises embedded in the architecture, in the IP architecture. It's kind of failed, including because of the incongruity between the architecture and the political economy in which it's embedded. Now that we know that, how could we design an architecture that takes that into account and takes promise theory as part of one of its tools?
Networks aren't just all around us, They're within us. They are us. Sometimes physical, sometimes virtual, they compose channels of influence to innovate and build. It's tempting to think of them as lifeless rigging, just cables, pipes, or tracks, but we should think of them as the pathways for opportunistic and adaptive change. Processes within processes. They trace out complex trajectories, amplifying, calibrating, packing and embedding, even thinking and reasoning. Networks connect the good, the bad, and the ugly. They need to be policed dynamically and semantically, for maintenance and for content, to keep the integrity of the system from harm. This is no simple challenge. Patching one location may cause another to come undone. The technology of our networks often outshines the science, but it's only when we have both perspectives that we can see our world for what it is. A web of processes that can either lift us up on a trajectory of progress or send us spiraling downward into background noise. We take much for granted, and now we need to step up to the challenge that bigger and faster bring. We need to understand smarter.